Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, rethinking the fate of Milky Way, the biggest map of the universe and a new eye on the universe. Rethinking the fate of the Milky Way. For many years, astronomers have believed that the Milky Way was destined for a dramatic fate, a direct collision with the Andromeda galaxy, our nearest large galactic neighbor. This idea has been deeply ingrained in scientific literature, documentaries, and public imagination, often presented as a near-certain event that would occur in roughly 5 billion years. The belief in this inevitable galactic crash has been based on observations of Andromeda's motion toward the Milky Way, detected through changes in the color of its light known as the Doppler shift, which reveals how objects move along our line of sight. However, galaxies also move sideways across the sky in what's called proper motion, or transverse velocity, and this type of motion is notoriously hard to measure accurately, especially for objects millions of light-years away. Previous studies typically assumed that Andromeda's transverse motion was minimal, which made a head-on collision between the two galaxies seem almost guaranteed. In a new study published in Nature Astronomy and led by Tilsoala from the University of Helsinki, researchers have now challenged this long-standing assumption by closely examining the uncertainties in current astronomical data and by incorporating the gravitational influences of other nearby galaxies. The study didn't rely on new observational data, but instead reanalyzed existing data from major space missions like the Hubble Space Telescope and the European Space Agency's Gaia mission. Unlike earlier work, this research emphasized the importance of including the full range of uncertainties in the measurements, rather than treating the most likely values as fixed. By running thousands of simulations and slightly altering the initial conditions, such as the relative speeds and positions of the Milky Way and Andromeda in each one, the team was able to explore a broader set of possible futures. When they repeated the assumptions used in earlier studies, they obtained the same results, a future merger. But by expanding the range of possible initial conditions, they uncovered a more nuanced picture. They also factored in the influence of two additional galaxies, the Large Magellanic Cloud, a massive satellite galaxy currently falling into the Milky Way, and the Triangulum Galaxy, also known as M33, which orbits Andromeda. These galaxies exert significant gravitational effects that subtly alter the motions of the Milky Way and Andromeda. The Triangulum Galaxy pulls Andromeda slightly closer to the Milky Way, increasing the chances of a future merger, while the Large Magellanic Cloud exerts a force that shifts the Milky Way's path away from Andromeda, making a collision less likely. With these complexities in mind, the study found that there's only about a 50% chance the Milky Way and Andromeda will merge within the next 10 billion years. In other words, it's just as likely that the two galaxies will never collide at all in that time frame. Depending on how the various gravitational influences play out, the galaxies might instead swing past each other in a close encounter or settle into a prolonged orbital dance without ever merging. This insight adds a new layer of uncertainty and intrigue to our understanding of the Milky Way's distant future. Even if a merger does eventually occur, it wouldn't be catastrophic in the way Hollywood might imagine. Stars within galaxies are separated by such vast distances that direct collisions between them are extremely rare. Instead, the gravitational forces would gradually draw the two galaxies together, reshaping them into a single, larger elliptical galaxy over time. If the galaxies do not merge, they may remain near each other in a sort of cosmic waltz, orbiting gently for eons without ever quite coming together. Both outcomes would reshape our view of the universe and our place in it, albeit in very different ways. The biggest remaining variable in this celestial forecast is Andromeda's transverse velocity. Even small adjustments in this sideways motion can determine whether the galaxies eventually merge or just brush past each other. Future measurements, especially as observational technology improves, will help to refine our estimates and clarify the Milky Way's fate. For now, the future remains uncertain, but that uncertainty underscores the dynamic and evolving nature of our understanding of the cosmos. Even when examining something as seemingly familiar as our own galaxy, there is still so much to discover. The biggest map of the universe. A major scientific breakthrough has just unfolded with the release of a massive new dataset, the largest map of the universe ever created, built using data from the James Webb Space Telescope. This monumental project, called Cosmos Web, is the work of a vast international collaboration of scientists who have now made their findings publicly available in the name of open science. The Cosmos Web field includes stunningly detailed images and a catalog of nearly 800,000 galaxies, stretching across almost the entire history of the universe, from the present day back to just a few 100 million years after the Big Bang. In terms of cosmic time, that's about 98% of everything that has happened since the beginning of the universe. One of the leaders of this effort, a physicist from UC Santa Barbara named Caitlin Casey, explained that their goal was to create a view of deep space on a scale far beyond anything previously attempted. To understand the scale, she compared it to a famous image called the Hubble Ultra Deep Field, which shows nearly 10,000 galaxies. If that image fit on a normal sheet of paper, the new JWST-based Cosmos image would be like a mural over 13 feet wide and equally tall, revealing far more detail and cosmic diversity. The motivation behind this enormous undertaking wasn't just to identify the earliest galaxies that formed after the Big Bang, but to better understand the environments in which they lived, the vast cosmic structures made up of dense regions and empty voids where stars, galaxies, and black holes first took shape. Scientists expected to see a few rare early galaxies, because the universe needed time to evolve after the Big Bang. Matter had to collapse under gravity, stars had to ignite, and galaxies had to gradually take form. But the James Webb Space Telescope surprised them. It revealed around 10 times more galaxies from this early period than anyone had predicted. It also uncovered previously unseen supermassive black holes, enormous regions of gravity so strong that not even light can escape, that were invisible to earlier telescopes like Hubble. In other words, it wasn't just more galaxies than expected, it was a new view of what those galaxies were like, how massive they were, and where they lived in the early universe. But as often happens in science, answering one big question leads to a dozen more. The discoveries from the Cosmos Web field have started to challenge the very models scientists use to understand the cosmos. One puzzling issue is that galaxies in the early universe appear to have formed far too quickly. Based on our current understanding of cosmology, it simply shouldn't be possible for them to accumulate so much mass, up to 1 billion times the mass of our Sun, in only a few 100 million years after the Big Bang. There are ideas to explain this, but no clear answers yet. This mystery is one of the most exciting parts of the new data. Scientists around the world are being invited to explore it further, and that's exactly what the Cosmos collaboration intended. A major aim of the project is to make cutting-edge astronomy more accessible. Although the telescope data was available immediately after collection, it was initially raw and difficult to work with. Only experts with powerful computers and technical know-how could really make use of it. For the past 2 years, the Cosmos team has been working to turn all that raw material into organized, easy-to-use images and catalogs so that scientists everywhere, including students and young researchers, can dive in and make discoveries of their own. They believe the best science happens when many different minds look at the same data in their own way. That's why the Cosmos team has made the full dataset available to the public, along with the scientific papers that explain it. And they're not stopping here. More observations are planned, and the team is going back to the Cosmos Web field to learn even more. They believe they may have already spotted the earliest galaxies ever seen, but now they need to confirm that by using a method called spectroscopy. This technique spreads a galaxy's light into its different wavelengths like a rainbow, revealing its chemical composition and allowing astronomers to calculate its true distance, which also tells them how old it is. In the process, scientists will also gain new insights into the chemical makeup of those ancient galaxies, studying key elements like carbon, nitrogen, and oxygen. This will help unlock the secrets of interstellar chemistry and offer clues to how stars, planets, and even life itself might have begun. Although these findings already push the boundaries of what we thought we knew about the universe, this is only the beginning. The universe is still full of mysteries, and thanks to this collaborative effort and the incredible power of the James Webb Space Telescope, humanity is now better equipped than ever to explore them. A new eye on the universe. On June 23, 2025, the world will witness the unveiling of the first images captured by one of the most advanced astronomical instruments ever created, the Vera C. Rubin Observatory. Situated high in the Chilean Andes, this observatory is set to revolutionize our understanding of the cosmos. For the next 10 years, it will capture hundreds of images of the southern hemisphere's sky every single night, creating the most detailed and comprehensive time-lapse record of the universe humanity has ever seen. This ambitious project is known as the Legacy Survey of Space and Time, or LSST. Unlike traditional telescopes that focus on narrow sections of the sky, the Rubin Observatory will scan the entire visible southern sky repeatedly, creating an ever-evolving portrait of the universe. Scientists will use this dynamic, wide-angle view to track cosmic phenomena such as supernovae, asteroids, black holes, and distant galaxies as they change and unfold in real time. Rather than presenting space as a series of still snapshots, the observatory will deliver an ongoing cosmic narrative, night after night. At the center of this endeavor lies a technological marvel, a digital camera of extraordinary scale and power. Roughly the size of a compact car and weighing over 3 tons, this camera boasts a staggering 3,200 megapixels, an image resolution so high that a single photo could reveal a golf ball from 25 kilometers away. The level of detail is immense. To view a full image in its entirety, one would need hundreds of ultra-high-definition television screens. To record the universe in full color, the camera employs massive filters, each as wide as a dustbin lid, that isolate specific wavelengths of light, from ultraviolet to near-infrared. The observatory itself has been more than 2 decades in the making. First proposed in 2001, construction began in April 2015 on Cerro Pachón, a mountain ridge in northern Chile. By October 2024, initial testing began with a low-resolution camera, paving the way for the main camera's first official images, which are now ready to be shared. The Rubin Observatory is not just a feat of engineering, it is a scientific mission designed to tackle some of the most profound mysteries in astronomy. One of its primary goals is to investigate the nature of dark energy, the enigmatic force behind the accelerating expansion of the universe. By measuring how galaxies cluster and move, the observatory will provide vital data for exploring this cosmic puzzle. Equally important is its role in mapping the large-scale structure of the universe and investigating dark matter, an invisible substance that makes up 27% of the cosmos. Dark matter acts as a kind of scaffolding for the universe, an unseen web that guides the formation and evolution of galaxies. The observatory is named in honor of Dr. Vera Rubin, a pioneering American astronomer whose groundbreaking research offered the first compelling evidence for dark matter. As a woman in a predominantly male field, Rubin faced numerous challenges, yet remained a tireless advocate for scientific integrity and gender equality. She passed away in 2016 at the age of 88, and the observatory bearing her name stands as a tribute not only to her scientific achievements but also to her resilience and legacy of inclusion. Beyond its contributions to understanding dark matter and dark energy, the Rubin Observatory will also keep watch over our cosmic neighborhood. It will discover and track millions of asteroids and near-Earth objects, playing a crucial role in planetary defense by helping detect potential threats long before they come close. Additionally, it will monitor stars whose brightness changes, which can indicate the presence of orbiting planets, further expanding our understanding of exoplanetary systems. The observatory will be poised to capture rare and dramatic cosmic events, such as neutron star collisions, which produce bursts of light and gravitational waves that ripple across the fabric of space. What sets Reuben apart, however, is not only what it is designed to discover, but what it might reveal unexpectedly. Some of the greatest astronomical breakthroughs have come from the unanticipated, mysterious flashes, strange motions, and phenomena never before observed. Because of the observatory's vast and continuous data collection, it may uncover new classes of celestial objects or even reveal unknown laws of physics. But this immense undertaking depends on one key element: the darkness of the night sky. Light pollution, particularly from satellite megaconstellations composed of hundreds or thousands of orbiting satellites, poses a serious threat. These satellites can reflect sunlight and create bright streaks in telescope images, disrupting the data and making analysis more difficult. While software tools can remove some of these marks, doing so adds to the workload, increases cost, and can reduce data quality. To address these challenges, Rubin Observatory scientists are already developing simulations to predict and reduce satellite interference. They are also collaborating with satellite operators to dim spacecraft or adjust their paths, ensuring clearer skies not only for Rubin but for future generations of telescopes and astronomers. The Rubin project is a global collaboration, led by the U.S. National Science Foundation and the Department of Energy, with partners around the world contributing to data processing and scientific interpretation. A significant portion of the data will be made publicly available, opening the door for researchers, students, and even amateur astronomers to engage with the findings and possibly make discoveries of their own. The unveiling of Rubin's first images will be marked by a global celebration, with events streamed live in both English and Spanish, allowing people everywhere to participate in this historic moment. For the scientific community, this is a rare and transformative milestone, an observatory poised to reshape our understanding of the universe, ignite public curiosity, and spark discoveries that will resonate through the decades to come.